do a little bit of a lighter lecture today. Over the past 2 weeks, we spent a lot of time talking about dielectric material, magnetic materials, and so on. And so what I want to do today is just give you a few examples of how to solve problems. I know we're also recording exercise classes, but this is more or less also a supplement. And today I just want to give a few kind of problems that I think are important as examples for you to understand how to deal with situations with dielectric materials or magnetic materials. So what I want you to do, and I'll give you a minute or two, but I really, for today, I want you to write along. Okay, see if you can follow along with the examples. So I'll be giving more pauses. It's a little bit more flipped classroom in the sense that what I'm going to do is give you some time to attempt the problems, and then we're going to go through it step by step. Okay, so I'll give you a minute or two. Grab a pen, grab a piece of paper, and be ready to write along. Okay, we'll get started in a minute. Okay, let's get started. So the first problem that I want you to think about and I want you to attempt is the following. This is a pretty general result, but nevertheless. So imagine I've got a particular medium. Sorry, two media and one boundary in between them. So this is medium 1, this is medium 2. This is epsilon 1 and epsilon 2 as their permeability. That's the right word. Okay, nevertheless, that's not too important, but so imagine I've got, in this case, I've got some, this is some normal, and the hat is here. And then what I have is I've got a particular field, an electric field pointing in this direction, making some angle with my normal. And so let's call this theta 1. And then what we see, what we typically see when some electromagnetic ray crosses a boundary, the angle shifts. Okay, so it could be, for example, in this way, and let's call this theta 2. And so the question that I have for you is, what is the relationship? You write it down. What is the relationship between theta 1, theta 2, epsilon 1, and epsilon 2? Okay, so this is the problem, and I want you to take a few minutes to attempt this question and see if you can come to at least more or less an answer. Okay, I'll give you 2 minutes to think about it, and then I'll start asking for tips and hints and stuff. Okay, let's go. Okay, I see a few answers popping up already. Is always a good sign. Okay. So, Xun Wang saying square root of epsilon 1 sine theta 1 square root of epsilon 2 theta sine theta 2. Alex is saying square root of epsilon 2 over epsilon 1 equals to cosine theta 2 cosine theta 1. And okay, so we have a few answers. So let's see how we would tackle a problem like this. Now remember again, you know, when we look at interfaces, right, when we go across boundaries, it is important to always just write down one very stable thing, and that's the boundary conditions. Okay, so let's just not do anything except for writing down the boundary conditions. So for dielectric materials, what is the boundary condition um, between say some medium 1 and medium 2? Okay, we covered this last time extensively. Um, there's one normal to the surface and one perpendicular to the surface. Can anyone tell me the boundary condition normal to the surface? Come on, people. What is the boundary condition normal to the surface? Okay, Harry's saying normal to the surface, D above minus D below is sigma F, the free surface charge, indeed. Okay, very good. So we can write this as a, in vector form, of course. We can write this as boundary condition 1, and that is that D2 minus D1 dotted with n hat equals to sigma F. Okay. Now we also have a second boundary condition, and that's the component parallel to the surface. What about the component parallel to the surface? Parallel surface, Harry again, E above minus E below equals to 0. Very good. 2 minus E1 equals to 0. Oh, sorry. Just write this in the vector form. Cross n hat equals to 0. Okay, so these are the two boundary conditions, and then the relationship between the angles and the various permeativities are relatively straightforward, because imagine I've got it in some angle, then in this case, well, the angle normal to the surface is just given by 1 cosine theta equals d2 cosine theta 2. Okay, and so writing this out, what do I get? I get that epsilon 1 e1 cosine theta equals epsilon 2 e2 cosine theta 2. Okay. Now, similarly, if I look at this one, second boundary condition, what I get an E1, right, 2, doesn't matter. Oh, sorry, I forgot to mention here. In this case, sigma F equals to 0. There's no free charge. Therefore, this one. So E2 sine theta 2 equals E1 sine theta 1. Okay, so this is boundary condition 1. This is boundary condition 2. Okay, so now, of course, I can combine this one. I can combine these two equations, and, well, I can get a relationship if I just divide this top by the bottom. If done well, I should, I think, get epsilon 1 cosine theta 1 sine theta 1 equals to epsilon 2 cosine theta 2 sine theta 2. Or, if you will, if you want to rewrite this, you can do epsilon 1 over epsilon 2 equals to this 1 over 10, so 10 on that side. So this should be tangent 1 and 2. All right? And so this is just a very simple example, right? It's just a refresher of how to get, the various boundary conditions. Now, of course, let me ask you the following question. How does this, how do the angles work? Is it a more shallow or less shallow angle compared to the incident angle if epsilon1 is bigger than epsilon2 or vice versa? Okay, I'll give you another minute to think about this. Okay, yeah, I always mark the angles wrong. Let's see. Get this wrong again. Yeah, okay. Change the angles. Okay. This one. Data 2, sorry, data 1. Data 2. That looks about right. Anyway, it just depends on where you define the angle, so that's not too. The difference in there won't be any difference in physics, but nevertheless, let's take a look. If epsilon is bigger or smaller, sorry, if epsilon1 is bigger than epsilon2, what happens then? And what happens when epsilon2 is bigger than epsilon1? So let's get a new page here. Over here. So I've got one like this. And so what happens when epsilon1 is bigger than epsilon2? Okay, let me give you two possible answers. One is like this, and one is like that. Sorry, I'll give you the color even. Pow! Okay, light blue or red? Red. Harry says red. How about the following? If you agree with Harry, raise your hands. If you disagree, um, I shouldn't say keep them lowered. Excuse. Okay. Raise your hand if you agree with Harry. Alex, Jason, Pearl, Shunchi. Okay, see more. Jack. Okay, getting more and more. Good. Okay. Yeah, and so the opposite would be true uh, for the other case. So let's make this epsilon 1 bigger than epsilon 2. This then becomes epsilon 1 is smaller than epsilon 2. Okay, so indeed, just taking a look at this form over here, when will the tangent? So if epsilon 1 is bigger than epsilon 2, that means that tangent theta 1 is bigger than the tangent of theta 2. And so, when is this tangent bigger? That is when theta 2 is smaller than theta 1. Indeed, this angle here is bigger than this angle there. Okay, and then of course in reverse we have this scenario over here. This to the middle of the page. Okay, so that is the first question. Okay, and so kind of hopefully this is a good reminder, refresher of boundary conditions. Okay, how do we set up the boundary conditions, and then what do we do in order to solve them? Okay, I'm gonna ask you something now a little bit more simple, and you know, let's do it. So, the very same vein, what about for magnetic field? Okay, so let's combine the two things. Let's take a quick break, but also during the break, you get time to think about this question. So let's go for a 5-minute break. Let's come back at 5:03. Okay. In the meantime, think about the the same scenario, but now with two media, one with mu1, one with mu2. How would the field change the angle in that case? Okay, I'll see everyone in a minute. Okay, welcome back. Let's take a quick look at the example that now you should have done for yourself. So let's make this 1, 8, 2. Okay, so now if I did the exact same thing with the magnetic field, what answers would I get then? So again, let's just get started with the simple stuff, or at least the basic stuff. And that is, what are the boundary conditions for the magnetic and the auxiliary field? What are the boundary conditions? Yep. So Pearl is saying H above minus H below is the surface current parallel. Very good. Let me write that down in a vector form. So that would be H2 minus H1, and then the curl of N equals K. Oops, no, I think it's the other way around. I think it should be this way in order to get the right directions. But okay. What about the perpendicular component? I'm gonna go for that one too, Pearl. Very good. Already in vector form. Excellent. So that would be B2 minus B1 dotted with N hat. And that equals to 0. Okay, very good. So in that case, we have the opposite boundary conditions, and what we can write, however, instead is B1 cosine theta, sorry, theta 1. B2 cosine theta 2, and also 1 over mu1 B1 sine theta 1 equals 1 over mu2 B2 sine theta 2. So again, if I divide these by each other, what do I get? I should get that it is mu 2 over mu1 equals tan theta 1 tan theta 2. Let's see if I did that correctly. Yes. Yeah, that looks more or less right. Okay, so a fairly simple exercise, a very simple problem uh, to uh, to to basically show that, how do I use the boundary conditions? What are the boundary conditions? Okay, let's go to the next. Let's go to the next question, next problem. The first one, the next one that I want to highlight is, okay, what is the energy kind of associated with the T field, or maybe I should say, what is the expression for what's the expression for the That's the expression for the energy in the field. Okay, in matter. Now, recall that for if no matter, then we get the results that looked more or less like 1/2 E multiplied with E tau. So how? What about the energy now? If we are talking about matter, let me start with the hint. Consider the charge. Okay, I'll give you again, let's say a few minutes to think about this. See, okay, recall what steps did we take to come to this result. The U is 1/2 E dot E integrated overall volume. And let's see if we can apply this. But now for the free charge, let's see if what answer we get. Okay, I'll give you a few minutes. Okay, let's. Oh, Alex is saying, is there something wrong for the last question in the last slide? Did I make a mistake? 1 over. Be if I do this tan theta 2 mu 2. No, you're right. Yeah. Excellent. Okay. Going back to this one then. So how much energy does it take for me to take some energy density through a potential? That's the same way we started with, getting the energy or the energy density for the electric field. That is by asking the question, okay, how much, uh, how much energy does it take for me to bring one charge into another situation? If you recall, what we did, if there's no matter, then Q is simply integral rho phi d tau. And we put a half here to avoid double counting. Right? So we don't want to count the charges or the charge density that also produces this particular capital phi. And so with matter, then the only thing I can really consider is the free charge, right? The charge that I have control over in the sense that I can add or remove. And so let's see if it's rho free, again, phi d tau. Okay, now do you remember the steps that we went through to get say from here to here? If you do, again, I'll give you a minute or two to work through it. It should be 2-3 lines to get to the final answer. Okay, I'll give you another 2 minutes. Let's take a look at the how to get to the equivalent expression of this. If I have E dot E, here what we do is our first identification of obviously the right, that I know the free charge density is just the divergence of D, and I got phi like this, then I make a slight trick. I look at the divergence of phi and D, tau, and then I have to minus that with the actual, so the gradient of phi tau. Now the first one, so this the first term here, we can rewrite this using Gauss's theorem. So this simply becomes a half E, well, phi dA, this, and the gradient of phi is minus E. Here I get delta with E, like this, d tau. And then, it's one last step to show that the first term disappears. Do we remember why? Well, if you recall, the D field goes as 1 over r squared, or even in its lowest order, it goes as 1 over r squared, and then phi goes as 1 over r, and the area goes as it goes as r squared. So this thing over here, this thing here is proportional to r minus 1. And so when you take this integral, which again we are free and we are at liberty to put this volume integral, therefore also the surface integral, anywhere we want, because if we're outside the source, we simply don't have the contribution, and so it ends up being zeros anyway. So we're just adding up zeros. So we can integrate this all throughout space in such a way that the first term disappears, and we're only left with the second term, d dot e, integrated throughout all of space. Okay. So the final answer here is just a half delta with e over space, all of space. Okay, that's another example of kind of how to look at situations where there is a dielectric material. Okay, is there any question about this? I take no as an answer. So the next question I wanna do, and this now we're starting to get a little bit into more complicated areas. Well, let me draw this out. Let's assume I've got some cylinder like this. And let's make this a conducting cylinder. Well, no, I don't like that. That's a little bit better. Okay, and so what I'm going to do is, and I'm actually going to fill this with a particular liquid. And I'm going to put another cylinder in here. A smaller cylinder submerged into this fluid. Okay, now let's handle a few items of business. This distance here is B. This distance here is A. Now, both blue and the green are conductors, but this one, I'm actually charging this up with a free charge of Q. Now, make this interesting. The height of this, and let's call the height of this is, let's call this H, and let's call this L minus H. Okay, now this liquid has a particular permeability. Let's call this liquid permeability. I don't know. Epsilon. And then the whole question is now geared towards something relatively simple. What is the electric field inside this material? Okay, as I told you, it's a little bit more complicated, but I'll give you a few minutes to look at this problem. Think about, at least at the very minimum, even if you're not super, you can't be that quick to solve this entire problem. Think about what are the steps that you would at least be taking. Okay, and then we'll go through it again step by step. Okay, I'll give you, let's say, 5 minutes to think about this. We'll be back soon. Let me fix some of the weird A, and let's also add in the fact that L is much bigger than A. Excuse me. And even that H is bigger than A. And this is so that we don't have to worry about edge effects and kind of the top layers. Okay, let's think about it. Okay, let's think about this problem, and let's set up our coordinate system first. Okay, so for example, we could set it in such a way that this, oops, don't draw it like this. Okay, so of course, we would be using a cylindrical coordinate system. So indeed, let's draw a coordinate system like this, and then some angle theta. It doesn't matter too much, but let's see. So here we would have some, let's say some theta, some r, some z. Okay, so we can swing theta around that way. Okay, so the first thing to think about, to realize is, okay, which direction is the electric field, right? So if we have this setup, at least we need to fill in to get some intuition, like what do we expect to happen visually. So in this example, which direction do I think the electric field is pointing? Okay, indeed, Punchunchi is saying it's radial. Indeed, right? So that's the first expectation. Now, from a physical perspective, what else do we expect to happen? So there's some radial field, right? Because there's some free charge Q introduced into this conductor. But when it's put inside a dielectric, what's the thing that typically happens? Boundary conditions applies to the interface, yes, but I'm really more talking about what is the physics behind it. Right? So when you have this field, something happens in the dielectric, right? So I'm immersing this cylinder in the dielectric. So what happens in the dielectric when I immerse some charged cylinder into this dielectric? Qualitatively, not quantitatively. Induced charges appear, yes. And then what do they typically do? These induced charges? Quantization, that's good. And so they typically end up shielding the screen the field. Very good. Excellent. Okay, so at least we have a mental picture of what to expect. And that's a good thing, right? So we know, okay, what's going on. Okay, now let's take a first step first, and let's write down that the E field in general, which is what we're after, of R phi Z is just given by the ER component, which of course, because of its symmetry, it should not depend on theta. It should just maybe depend on R and Z. And then we have already considered that the field is radial. It must be radial. And so in this case, I am looking at only the R component. Okay, now let's consider some of these boundary conditions, for example. So we have a few boundaries here. So let's do the easy boundary first. What about the boundary between the dielectric liquid and vacuum? So in that case, The top part, we assume it's more or less vacuum. What happens? What happens there? Okay, so one thing that we can look at is, okay, we know that the field, the electric field, ought to be radial. Then between the interface between the liquid and the vacuum, which way is the field pointing? Right, that should still be, parallel to the field itself, right, to the surface itself, because the E field is going in a particular direction like this. And so when I cross this boundary in this E field, even though this whole thing is still charged, the expectation is that there is no there is no discontinuity in this case. Okay, and so we can even remove the dependence on Z, right? Because in this case, L is much larger than A, so we're really talking about a very kind of a thin thing. And when we make that long, we also generally don't have to worry about the Z direction. We're mainly dealing with some ER, right? The field parallel between liquid and vacuum. Okay. In that case, we don't see any discontinuity in the field in the Z direction, and we expect it to just go just to be the same everywhere. We only have a radial component. Only have radial component that depends on R. R. Okay. So now we are more or less in business. Okay. So what let's look at the first subproblem. What is the surface charge density at the let's call this at the at the top side here. Let's call this medium 1, and this is medium 2. What is the surface charge in the region 1, right above the liquid? Right, when we think about the boundary conditions, um, how do we set up in this case, or how do we know how much surface charge density there is in the top part, which is vacuum? Anyone? Remember the boundary condition that we had before? So we take a look at this one here. The boundary condition. Now, of course, we know that the now this is just a conductor. And so what we're really looking at is that in region 1, surface charge density is just epsilon naught r. Okay. Now, of course, at the surface, so r equals a. R equals a. Okay, now what about in the second one? What about in the liquid? What is the surface charge density? Okay, the expression should look very similar to this one. Anyone? So again, here we look at D above, D below. There is no below. Well, there's a below, but there's no field in there because we're talking about a conductor. And so here we are also looking at that D above in this case. So into the liquid equals to just sigma, right? Because we're looking at the normal component here. So here we just have epsilon ER divided by A. Okay. Now, the two of these are related to each other because they are bound by the total charge. Right? Somehow we must be able to balance this. And so Q, right, the total free charge, is, well, how much? Well, that's just the amount of charge on both sides. We have to calculate what is the total surface of the part that is sticking out of the liquid and then the part that is in. So we can write that the circumference is 2 pi a, and then times the height. This would be sigma 1 h, right? Because that's how much total charge there is. Given 2 pi a h is the amount of surface that corresponding to sigma 1, and then similarly we can do plus sigma 2 L minus h. Now we can do a little bit of algebra here, and so look at the total charge Q equals to 2 pi a epsilon naught e, function of r, but again only at the surface, right? Because we're looking at the surface charge density, the two expressions given here. So we get this one times h plus epsilon r, and then L minus h. Now I can rewrite this as 2 pi a, and if I just take the epsilon naught ER out, and what I get H plus, and now here, this here becomes epsilon over epsilon naught, which we can call epsilon R. So this is the relative L minus H. And then finally, actually simplify this a little bit more. So this becomes 1 minus epsilon R times H minus epsilon RL. Okay. And now I should again note that these here is ER at R equals to A. Okay, so we can reshuffle this in such a way that we can now write that ER R here, R equals to A, just Q divided by the rest. That would be 2 pi A epsilon naught, and 1 minus epsilon R n minus epsilon L. Okay, so now I'm in possession of knowing the electric field, but only at the boundary. Okay. And so of course that is not entirely satisfactory. And so here we must first think about um, we must now first think about what is inside the um, what is the field inside the displacement field inside. Okay. So let me give you another few minutes to think about how do I get the field inside now. Okay, I'll give you a few minutes and then we'll come back. Is it plus epsilon naught? Yes. Yes. Good job. Now that we know what the thing is on the boundary, we can see if we can try to get it for the rest. Okay. So again, give you a few minutes to think about how to get for the rest of the dielectric. Okay, does anyone like give it a crack? So what would be the thing to do now? And we've looked at a boundary condition. What would be a natural next step? Okay, so one way you can do is you can think about the entire the problem that we solved in the problem sets. Remember that we just set up the most general solution that we can, and then we try to solve for the potential, and then so on and so on. Now, of course, in cases with obvious symmetry, we can do slightly better, and do a little bit better. And so one thing that we can do is to look at to draw um, a Gaussian surface around it, and then ask, okay, well, what is the how does the field relate in that way? So in this case, what should I do? Well, I could write down. I could now draw. If I have a cylinder, this. Okay, this is the original smallest cylinder. Okay, so now I'm drawing some surface around it like this. Drawing some surface around like this. Okay, so draw a Gaussian surface around like this. And one thing that I do know, once I've done this, is if I integrate over the red one, so in this case, what I can do is I can look at the radial components. So just to say that 2 pi r, and let's make this r, this size r, this size L. Do I now have 2 pi r L, and E is of course perpendicular to it. ER as a function of r equals Q total over over epsilon naught. Okay. Now in this case, why am I doing this? Why am I needing to do this? And that's purely because I have this E field which is composed, right, which is contributed by the total charge. So Q total is actually just the total charge inside the surface. Inside the surface, this includes free and polarization charges. Okay, and so I could now continue to use this, right? This expression here. But I know that this expression here must match when the boundary is when we have at the boundary as well. But here, what I can write is that, as in the limit of r going to a, right? When I shrink this all the way to a, then r simply turns into, let's see, properly. So that is a, so that is just 2 pi 2, right, 2 should be below here, and q total over 2 pi epsilon naught al. Okay. So of course this total is just q. In which case, what do I have? I have that er is a function of r is er at a over r. And so, by matching the boundary condition, I now have that. I now have the following. I have that r is this. Oops. R is a function of r. Right? We had an expression given here, which is just a over r of this expression over here. And so I can just copy that one, but replacing a with r. So let's see if I've done it correctly. And it must look something along the line of this. Q over 2 pi epsilon naught, let's see, pi epsilon naught r, and then it's 1 minus r h. It's 1 minus epsilon r h plus epsilon r l. That is correct. Yeah, that looks more or less correct. Okay. And we are now with it. We have now the expression for the field inside inside this system. Okay. So at this point, are there any questions? And one thing that you can do is, of course, you should be able to now also, when we look at this question over here, you should also be able to calculate what is the energy basically inside this field. Okay. So that's another thing that you could do. Okay, but I'm not gonna. It's a lot of just algebra where we just have to integrate these two fields over all of space. And you can then use cylindrical coordinates to do the integral, as you end up integrating parts where there is dielectric material, and you end up integrating parts that there's no dielectric material. And so you end up with just a general expression for U. Okay, but you can see, right? It's the crucial thing, of course, is make sure you've identified your boundary conditions, and then make sure that your general solution matches those boundary conditions. If there are easier ways to obtain the form of the field or of the potential, just use them, and you're good to go. In the worst case scenario, you only have the broad symmetry, and you can use the most generic solution that we've looked at when we looked at boundary value problems. You can do it that way as well. Of course, you can also use method of images, right? That's what we looked at last time around when we placed images in different sides. Okay, so the last thing that I wanted to mention is something a little bit related to the problem set. I don't know how many of you have started looking at the problem set. There's one problem where you're asked to look at a dielectric material that is placed inside a uniform field. Okay? And then the question is, what happens there? Now, for those who've kind of started working on this problem and have also started reading, for example, Griffiths, will have seen possibly a difference, because I asked you to show this in a particular field. So why don't I go through the example in Griffiths, and then also I can point out where there is the actual difference. Okay. So again, in Griffiths, in the problem set, you're being asked, okay, so we've got some sphere, dielectric sphere, and there's some electric field, 0 inside. Okay, what is the what's the field inside of this dielectric material now? So in order to solve this problem, again, we need to first consider boundary conditions. What are the boundary conditions that I've set up? So let's call this something with epsilon. And then the second thing is, okay, well, what is the solution that I need to match this boundary conditions on? Okay, now we've seen all of these boundary conditions. I'm not going to rehash them. And in the interest of time, I'm not going to, this is the one that I'll just immediately go step by step. But the boundary condition 1 is, of course, that the potential, let's call him V. So V inside is the same as V outside, right? So the scalar potential remains the same. The second thing is that the D field is has a discontinuity depending on the free surface charge, but there is none. But still, the displacement field still dictates that epsilon partial V partial R, right? Because the surface is normal to R, is epsilon out divided by d by dr. Okay? And the third one, of course, is that V out tends towards minus E0 R cosine theta for big R, right? So far away. So we have these 3 boundary conditions, and the system can then be relatively easily solved, because we now need to look at what is the most general solution for this system. If you because this is a sphere, and we have a complete symmetry around the phi angle, we have that the most general solution is given by V r theta phi, the sum from L to 0 to infinity of A L r to the power L plus BL, and then r minus L plus 1, and given P of L as a function of cosine theta. Right? Remember these Legendre polynomials, and remember this most general solution. So this is the most general solution, and so we need to figure out, okay, what is the appropriate one to use inside, and what's the most appropriate one to use on the outside of this of this space. On the inside here, we must only consider the ones that do not blow up at r equals 0, right? The solution must exist, and therefore on the inside we have V side r theta equals to the sum of L0 to infinity AR r to the power L as a function of cosine theta. Okay. Now similarly on the outside, so I have that V out equals to, and here comes the trick. I know that very far away it must reach e to the 0, e underscore 0 r cosine theta, and so that's a term that I must have as well. So that very far away I reach this. There are no other r terms because I actually know that the Legendre polynomials are orthogonal with each other, so it cannot be some cosine squared or other higher orders that I have here. So for the positive, right? So for all the ALs, they don't exist anymore, but the other series I need to take into account as well, which is the 1 over r ones, which in this case, because I'm not considering the inside of the sphere, I must take into account as well. I have all the other terms here, RL plus 1, PL, like this. Okay. And so of course, for this one, when I take R going to infinity, all these terms can still exist because the thing that it must lead towards is already here on the left-hand term. Okay, and so once I've set this up, it's fairly straightforward. I have my boundary conditions, and I have my most general form, and so I can just equate things with each other. So I'm not going to go through all the excessive details of the algebra, but for example, if I apply boundary condition 1, I get that the sum of from L to 0 to infinity of AL big R, right? Because here we're on the surface, R equals to big R here. And so A to the big R L PL equals to minus E naught big R cosine theta plus the sum L from 0 to infinity. And then we have BL divided by big R L plus 1 BL. Okay. And so here we must have that all of these are individually. So each of the L's must agree. We end up with two equations. So this is AL RL equals to BL AR to the power L plus 1. L is not 1. And then A1 R equals to minus epsilon naught big R plus B1 over R squared for L equals, in this case, sorry, this is L equals to 1. L equals to 1. Okay. I can do the same thing, but I can now, I need to differentiate this. If I differentiate this, I get another condition, but now with on the left-hand side epsilon, on the right-hand side epsilon naught, and then I end up combining these two in such a way that I get the coefficients out. Okay. So just as an example, if I do this and I do boundary condition 2, dot, 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 then, I should, if you do this, again, please do try this at home. You can AL equals BL equals 0 for L is not equals to 1. And then you get A1 equals to minus 3 over epsilon R plus 2 naught, and B1 equals to epsilon R minus 1 divided by epsilon R plus 2. And let's see, this is R. Okay, I can't even read my handwriting. Maybe R cubed. I need to double check this, but okay. I'll fill this in right now. And so you end up with just the final answer being, this correctly, maybe 2, I think. And so V on the inside should be minus 3 epsilon 0 epsilon R plus 2 R cosine theta, which is just the same as minus 3 E0 over epsilon R plus 2 Z. Okay. And so here, for the total field, here is E. It's just 3 over epsilon R plus 2 naught. Okay. Okay. Now this is the result that you were supposed to show also in the problem set. Now, why when you're asked to show the electric field for the polarization, it looks nothing like all these potentials and things that you've done here. And that's because in that question over there, I'm asking only for the field due to the polarization. So in that case, E inside is E0, right? It's the original field plus the polarization, field due to the polarization. Okay? And so indeed, if you end up doing this, you end up with the key result, which is actually part of what you have to show as well. You end up with this question, this expression over here. Okay, so it's just a caveat for when you're doing problem set 8. Okay, so same problem, slightly different method. So you're not being asked to do all of these tedious steps, but instead go directly to the field due to the polarization. Okay, so that's all that I wanted to show today. I hope this was a little bit helpful for you. Again, to give you a little bit of a sense of guidance in how to do questions when materials are involved. Okay. Next, the coming Thursday, there will not be a lecture, right? We will not, it's going to be the graduation ceremony. So there's not going to be any online lessons. We're going to continue next week, Monday. If somehow, because of these missed lectures, we end up being a little short on time, I'll make sure to record extra videos that then you can follow. But it should, because we still have 2 weeks left after. So next week and the week after, we still have 2 weeks left to do the time varying fields and the wave equations, and that should be more than plenty. Okay. In that case, that's it for today. Thank you very much for coming. So you're happy to free to go, or stick around if you have any questions. Okay. See you next week. So this thing that seems that V inside not equal to V outside. You don't necessarily need to even calculate V. I don't know why you end up with a V that you think is not. Okay, that's what you mean. Okay. Is it not the same? It is the same. And R equals A. Oh, the epsilon, that's what you mean. Okay, let me quickly check if I there's a bit of a boo-boo here. Check this. They have made a boo-boo. Yeah, that should be epsilon naught. That's right. Let me fix that. Okay, yeah, Isaac, remind me to. Oh, Isaac is there. Yeah. Yeah. Okay. I'm gonna take one question at a time. So Alex is saying I got issues with problem set 5. Do you want to type it out or say it out loud? But why don't I, in the meantime, answer Poon Chun Chi's question first? Okay. Let me see. Homework 8, question 2. Do we treat those coils like bounding around something like a toroid? You don't need to. It really is just like the picture that you're being shown. It just has n turns. Okay. No, in this case, it's just assume it really is just a just causing a uniform field in there. You don't have to take into account the curvature. If that's the question you're asking. Alex, you have your question? So, Ling, as I was saying, we will make sure that before the 22nd, we will have it. So, let's aim to have it circulated, you know, before the end of before on Friday. It gives you 2 days to think about. If that's okay with you, then we'll try to have it by Friday. Okay, let me go and check which question you're talking about. Problem set 5. 1A. Okay, give me a quick second to get that question up so I know exactly what you're talking about. Okay. Okay, here it is. Multiple expansion B1A. Click on it. Okay, so basically the general formula in this case, what is meant here is that you have to leave V as a function of Y. And then the next question is, find it explicitly when V as a function of Y is now constant. Okay? So you still have to use, as much information as you've been given, but because you're not given the exact form of V0 as a function of Y, then that's what I meant with find, under the circumstances, the most general formula. Right. So that's exactly what Isaac is saying. So the question asked is, in that case, is, if V of 0, V0 as a function of Y is unspecified. But look, if you got everything right in the end, then we can see if we can give you some extra points for that. But it yeah, let me talk to Isaac and let's see if we can fix that. If it's in question, if it's in part B, I'm sure we can work something out. No problem, no problem. It's not a problem. Okay. Any other questions? If not, let me stop the recording.